Perspective is one of the most important ways that we talk about art and photography. Like many people, I learned it in my art classes, but it's clear that the conventional story around perspective is the whole story. In this talk, I'm going to explain perspective in a new way that I think can help us really understand how pictures work in a much better way from what many of us are taught. And to do so, I'm going to draw together ideas from art history, but also recent new ideas in psychology and neuroscience, as well as computational photography, to help us give us a better understanding of how exactly perspective works. A few years ago, I started spending a lot of time drawing pictures of outdoors, and I would sketch pictures like this, and I would also take a photo with my smartphone, so I have it for reference later on, like if I want to keep working in the picture. And I started to have this experience where if I compared the two pictures side by side, my first gut reaction is, well, my drawing doesn't look like a photograph, so that means I'm a bad artist. And I don't actually believe that, but that was my gut reaction. But then I would compare the picture on the screen with what I was seeing in the world around me and realize, well, actually, these things look really different too, or they feel different. The appearance of the picture on the screen feels very different from the way the world looks around you. And if you haven't done this, I recommend trying this outdoors yourself. And so this led me down the road of trying to understand, how do we understand shape and space in pictures when we as humans look at a picture? And in order to come up with answers to this question, this involved in looking into how we understand shape and space in the real world. Because it turns out that there are some important aspects about how we understand how our human vision works in the real world that are so very surprising and not obvious. So when I talk about perspective, more generally we talk about projection, and geometrically we can think about there as being some mapping from points in 3D space to points on a 2D picture plane. And the question is, when we as humans look at a picture, what constraints do we have about the possible 3D locations given the 2D locations on the picture? And I'll say a little bit more about what I mean by that. So the most common notion of projection in the class of picture projections is linear perspective, which was developed in the Renaissance by Brunelleschi and Alberti. And these original notions of perspective are really drawing techniques. And the basic idea of linear perspective, which you may have learned in art classes, is that you place down one or more vanishing points, and then you draw a bunch of straight lines that connect to those vanishing points. And this gives a set of rules and guides that can help you make more realistic pictures for scenes that have rectilinear or axis-aligned lines. When this was developed in the Renaissance, it took artists a while to figure out how to incorporate it effectively into compositions. So this earlier use of perspective here looks like a bunch of people painted onto billboards on a big grid in the matrix. One of the most famous effective uses of perspective is the School of Athens here by Raphael, where the architecture is carefully depicted in one-point perspective and the individual characters seem well integrated into the architecture. Nowadays, our photography and smartphones and other kinds of photography primarily use linear perspective. So this is the most widely commonly used notion of perspective. And you can tell these pictures are perspective because the parallel lines in the world converge to vanishing points. But even though linear perspective has dominated our conversation around how projections work in pictures, when we look through our art history, we see many other approaches, including prehistoric cave art and ancient Chinese parallel perspective and various uses in modern contemporary art, where people do all sorts of other things. So linear perspective is the most well-known technique, but when you look at what artists do, there's so many other approaches to depicting space. The idea behind linear perspective is that a picture should have a particular location where if you put your eye there, looking at that picture should be the same as if you were looking through a window. The same rays of light reach your eye. So geometrically what that looks like is there's a point called the center of projection, and to project a point from 3D space onto the picture, you draw a straight line between the center projection and that point, and the intersection is where that point projects to an image space. So conversely, as a human viewer, when you look at a picture, if our vision assumed that that's how pictures work, then the way you would interpret a point in 2D is that the corresponding 3D location has to live somewhere on that line. But it could be that human vision makes some other assumptions. And so again, my goal here is to describe what are the constraints by which humans could project from 2D pictures to the world? And what 3D positions could we infer from a 2D picture? Now, in order to understand these constraints, it's worth studying the limitations of linear perspective. And many of these are well known, at least within some areas of art and psychology. The most well-known kind of distortion are distortions that come from wide-angle pictures. So, for example, in this photo, this is just a photo that came up on my smartphone, the man and the basketball at the center look undistorted, but in the corners of the pictures, the basketball and the man are stretched out in what's called marginal distortion, because they're at the picture margins. Another kind of distortion that occurs is confusingly called perspective distortion. And here are 4 photos of the same person taken with different zoom and camera positions. So basically, when Emily Cooper took this picture, she took a photo at one zoom length and then moved the camera closer and then zoomed out and so on to produce the same image-based shape of the person. So the person's appearance looks quite different. And of course, you can get lots of nice fun effects with these kinds of distortions that, I could watch this video all day long. Now, when people talk about these distortions, the conventional explanation for why they look distorted is that we're not looking at the picture from the center of projection. So then where is the center of projection for this picture? Well, most people wouldn't figure this out unless you study the literature and work it through. Basically, for this picture, it's in front of the magenta cross at 2/5 of the image width in front of it. So for example, if you're viewing this on a cell phone screen that's 5 inches wide, then your eye should be 2 inches in front of the cell phone screen. Or with a large monitor, maybe you should be about a foot in front of the screen. And people do not view pictures this way. Now, if you do put your eye in the right place, then the distortion does go away. Now, and one caveat here is you have to do this with one eye open, unless you're stereo blind. But if you do that, then the sphere does project to a circle on image space. But again, people do not view pictures this way. This is called wide-angle photography because the angular field of view from the center projection is much wider than the field of view that the picture has from normal viewing position. We view it from a much different position than the picture's center projection. And so this indicates that we just rarely view pictures from the focal center, even if they have focal centers. We see giant faces projected on billboards. We see huge landscapes on our tiny little cell phones. So we just don't view pictures from the center projection, even when one exists. What's more, sometimes there's an assumption that artists do use linear perspective. Martin Kemp, the art historian, surveyed the large collection of the Ashmolean Museum in Oxford, and he found that only 3% of classical paintings there strictly followed linear perspective. And now this is, in applying the linear perspective construction drawing rules, but again, it's very rare that people strictly follow those rules. And in fact, there are many great artists through history who are known to have been excited about linear perspective, embraced it, tried it out, and then discovered it has lots of problems and eventually abandoned it or did not follow it strictly. And examples include Leonardo da Vinci and Turner and Hockney, all of whom wrote extensively about the problems of linear perspective. And in fact, when we look at this most famous example, the Raphael's School of Athens, and we look down in the lower right corner here, we can see that the philosophers here are holding 2 globes, and these globes are circular in the image. They're not stretched out the way that they would be if the picture strictly followed the linear perspective of the architecture. What's more, none of the faces are stretched out either. And in fact, if you work through the stretch implied by the architectural perspective, then it would look roughly like this. But Raphael did not draw it this way. And so Martin Kemp, the art historian, says artists use linear perspective as a working tool that delivers convincing results when used pragmatically, but they don't follow the rules slavishly. And he's specifically referring especially to Renaissance artists who use perspective. And so I would make a more specific claim, which is that realistic wide-angle painting is usually multi-perspective. That means that these spheres and these faces are being depicted with a different linear perspective from the rest of the picture. And in fact, the art historian James Elkin has written that the Renaissance artists actually don't necessarily seem to think about perspective as a single perspective for the whole picture. Vasari talks about perspectives in plural, not singular. And when we look through large pictures throughout art history, we see none of these faces are stretched in this extremely wide-angle scene, or in this very different approach to perspective. Again, all the faces have that similar look, as if they had been, as if they had their own perspectives. So let's talk more about multi-perspective. And there's lots of interesting examples from photography and computational photography that can provide some insight. So here's Fredo Duran's holiday card from a few years ago. And the way he made this was he photographed his family inside of this cardboard box over and over again, and then manually composited the results into a single picture. And it looks like a totally fine picture. It doesn't look particularly distorted, even though each of the different cubbies in this picture had its own vanishing point. Here's an example from 20 years earlier, and it's a sort of a street view kind of scene. And it appears that the photographer manually composited a set of parallel photographs to each other. And you can see that the scene has multiple vanishing points. The buildings look a little trapezoidal, whereas they're not in real life, but otherwise it doesn't really look distorted. And I trace this idea of multi-perspective as a generative technique back to a paper by Manish Agarwala and Dennis Oren from around 2000 at Tomorrow Monster, where they use computer graphics techniques to simulate various kinds of painterly multi-perspective techniques. Here's a computational version of that, with an algorithm that where they took a bunch of photographs of a street in Antwerp and automatically composited many, many different photographs that all have a parallel linear perspective to produce a very undistorted looking street scene. Here's a different variant of that, where again these photos have a dolly zoom relationship, so the camera is moving forward or backward while zoom is adjusted, and then the pictures can be composited to produce a new photo in which the zoom for the mission in the background is different from the people in the foreground. Another fun example of this is from an animator who worked on the movie Encanto. He wanted to get a particular zoom on the characters, but also a relationship between them, and the graphics software only supports conventional linear perspective. So to achieve that, he just distorted the geometry. One other application which is worth mentioning is if you take a photograph in the Google Pixel phone in ultra-wide mode, and there's a face in the corner, then it will apply a different projection technique to these faces. This is from a paper by Yicheng Shi, published in 2019. And you can see that in this ultra-wide, this wide-angle photo here, this person's face is not distorted with marginal distortion. That's because the phone's camera is silently applied in this computational correction. But in doing so, it creates other distortions around the face. Then the string should be straight, but it ends up being curved. So with all these examples in mind, we can start to describe when things look distorted and when they don't. And the first statement I'll make, I'm going to call this a hypothesis or really an observation, and call it shape locality. And the statement is that once we recognize objects in a picture, the shape that we perceive for those objects within any small picture region does not depend on the rest of the picture. So let me tell you what I mean. If you look at this picture here, there's a red car that gives you some sense, and you have a sense of what the shape of the car is in the picture. Now, if I just crop out the picture and only show the car, your sense of that car's shape does not change. Or if we put some new environment around it, that it looks very curved and nonlinear, again, the perception of the car's shape is also unchanged. So the perception of shape only depends on the local picture content once you've recognized it. Now, this observation rules out most projection systems for how human vision works. In linear perspective, the appearance of an object should depend on where that object is in the picture. And clearly that's not the case, so human vision is not assuming linear perspective. And the same goes for nearly every other mathematical projection approach that people have come up to explain perception. Now, just to be clear, this is about the internal shape of an object, not its relationship to other objects. So here, the fellow in the middle versus in the very lower right, they look like they have the same shape, but very different sizes, very different relations to the rest of the object in the picture. In this case, again, like I mentioned, it depends on recognition. So depending whether you perceive this as a person running away from you or a dog running towards you, you get a different sense of what the shape would be. But once you make that decision, or your vision system recognizes the object, then the shape does not depend on the rest of the picture. So again, within any picture region of a picture, once we recognize the objects in that picture, our shape perception doesn't depend on the rest of the scene, on the rest of the picture. So I want to characterize a little bit more now when perceived distortion, when things look wrong. And I want to make one note about the terminology. I'm talking about how things look. I would say that we have a sense of when things look like. Often people use the term distortion to refer to optical distortion, flaws in camera manufacturing, and that's not what I mean. I'm really referring to the sense when we look at a picture like this, we have a sense that doesn't look like a normal basketball. It looks stretched out. We perceive distortion. And what's more, I would claim that not only do we perceive distortion, we have a mental sense of what shape this picture is referring to. That we see this is a stretched out version of a normal volleyball, not a normal picture of a stretched out volleyball. And in fact, this tension between the depicted shape, the perceived distortion, and the known underlying shape can, be amusing and has some entertainment value. So there's some tension between multiple visual representations going on. And key observation to make is that objects never look distorted at the center or near any part of the middle of a linear perspective picture with a reasonable focal length. And this is based on a hypothesis called the direct view condition, based on a paper from SIGGRAPH by Dennis Zorn and Albar. And I'm going to restate this in a much more precise and perceptual way. And so my statement of the direct view condition is that a picture region looks undistorted if it looks like it shows a normal object at the center or near the center of a normal linear perspective picture. So a basketball at the center picture looks circular, and so any circular basketball or circular sphere looks undistorted, and one that's just oblong and stretched does not look distorted. And this generates a bunch of conventional rules. Spheres should project as circles, straight lines should be straight, faces should be essentially symmetric and not stretched out, and so on. When lines are not straight or spheres are not circular, then they look distorted. And that describes why nothing in this picture looks distorted, because each part of this picture is near the center of its own local linear perspective projection. In this picture, the ground clearly looks distorted, but if we just focus on the Eiffel Tower, this local part of the picture doesn't look distorted because it looks like this could be the center of a linear perspective projection. In this ancient Chinese parallel perspective projection, each individual person does look like they could be at the center or near the center of a linear perspective projection, and so they don't look distorted. This corner of a building doesn't quite look like what a right angle here in a building cannot project to a picture like this, so it looks a little distorted. It's a little off. And this is a little bit borderline. You might either view this as a stretched out picture of a face or a picture of a stretched out face. So to test this hypothesis, we ran an experiment as follows. We built the computer graphics seen on the left, which has a big volleyball in the right-hand corner, and this is a very wide-angle linear perspective projection. And we also rendered a version of it where the volleyball had its own local linear perspective according to the direct view condition. And we show these to people, and we ask them which one looks more like a volleyball, and they all say the one on the right. We tried this with a variety of different projection techniques. We got similar results. Now, interesting with parallel perspective projections, the volleyballs look pretty similar, and here people are 50-50. Both of them basically look okay. And so we actually saw a correlation between the degree of preference people have and the amount of asymmetry or the aspect ratio of a volleyball in 2D. And so the really stretched out ones, people really they don't look like volleyballs as compared to the perspective on the right, whereas the parallel one, people are actually a little bit below 50-50. We've also developed recently a new paper, a new technique for unwarping wide-angle pictures called MADCOW. I love the acronym this Kevin, a collaborator, came up with. It's Marginal Distortion Correction for Wide-Angle Pictures. And so basically what you do as a user is you annotate regions you want to preserve, and straight lines are important, and it can generate an output that applies a direct view condition to produce local linear perspectives that don't look as distorted. And our method is far from perfect, but it really illustrates a technique that could be improved in future work. And it really demonstrates the power of the direct view condition as a principle for removing distortion. Here's another example. The left is a wide-angle photo, the right is our correction of it with the two people on the ends. And you can see that the person on the left there looks very stretched out versus our correction. And I think he would probably prefer the picture on the right. So the direct view condition describes the phenomena well. It describes when things look distorted and when they don't. But why would that be? Why does human vision work that way? And in order to have answers for that, we need to now switch gears and talk about 3D vision. How do we experience the world in 3D and not just in pictures? And I want to begin with this example here. This was developed by Professor Michael Cohen, and it looks like a normal photograph. And I'll give you a moment to look at it and spend some time studying it. And what I want you to do is try to see, where does it not look quite photographic? What here is not like a photograph? Some people might say it's a spiral by the couch there, but that's not it. The key observation here is that this is actually a video, and almost everything in the object in the video is changing. So here's the first frame of the video, and here's the last frame, and they look really, really different. And you can pause this video now and scrub through it, and you'll see that it's actually really changing quite a lot. And so why is that? So again, here's the video again. And when you look at something as changing, at the moment that it's changing, you can see it changing. And so like the curtains right now, I think are fading out a little bit. And the rug now is fading out. And so if you stare at the rug right now, you will see it fading out. But if you look away, you don't notice these changes. So it's only when you're looking right at it do you see these things. Here's the home screen from my cell phone a while ago. And at some point, after I started, studying this problem, this topic, I started looking closely at lots of different things. And here I noticed, the second hand on the clock icon is moving. And I'd never noticed that before. And how long has that been going on? And I looked it up, and it's been 13 years since they implemented the second hand moving on the clock, and I never noticed it in all that time. And when you look right at it, it's really obvious. So these are phenomena called inattentional blindness, and it's very related to change blindness. There's an example illustrated on the right where you're supposed to track a volleyball and a gorilla appears that many people are familiar with. And these are really interesting phenomena. And where do these come from? And one of the sources that it turns out is a cause of these phenomena is something called foveal vision. And if you're not familiar with it, it means that when we look at something, we're getting most of the information in the direction our eye is pointed. So for example, when I took this picture here, there's some street signs over there in that red box, and I could, even though they don't show up in the photo, I could see them if I looked right at them. And in fact, what I want you to do here is fixate your eye on any one of the street signs and try to read the text on a different street sign. And I bet you can't do it. Whereas if I just ask you to read the street sign, your eye will move that street sign, and you'll do it without thinking about it. It's no problem to read these things, but once you force your eye to fix it on one spot, you can't read the text elsewhere. So a lot of people know about foveal vision, know that it's that we get most of our information in the direction we're looking, but it's not as well known just how small foveal vision is. So the rule of thumb for foveal vision is you hold out your thumb at arm's length, and the width of your thumb is the extent of foveal vision. So it's really small. So here, when I photographed this picture of my dog in the park, I could see the expression on her face, because she was within the extent of foveal vision. She was far enough away that she was entirely within foveal vision. But you look in any other direction, you can't see that detail. I have one more demonstration to show here. This is from a paper by Rachel Brown et al. And what I want you to do is to stare at the red dot, and now keep staring at the red dot and follow it with your eye as the dot moves. Okay, now feel free to move your eye however you want. And what you should be noticing here is that as long as you keep following the red dot with your eye, the picture looks static. But in fact, the picture is actually changing in the parts that you're not looking at. So as long as the authors here are very careful to modify the picture in particular ways that we would not notice in peripheral vision. And in all these things, my thinking here is very influenced by work by Ruth Rosenholz, and she points to this illusion of awareness, that we're unaware of how much information we lose in peripheral vision. So not only do we not know what we're missing, we also don't know that we're missing anything, and it's surprising when these things are pointed out. Now, there's one other surprising aspect of human vision in the real world I want to get to before we get back to perspective. And that's the question of how much 3D awareness do we have of the world around us? How much 3D geometry do we store of the world that we're looking at? And because we have this feeling that we're building a 3D model of the world in our heads. We move through it essentially with like this computer graphics model of the world around us. And my favorite demonstration that that's not true is something called redirected walking. Redirected walking is a technique in virtual reality. It solves a problem where you want to have someone walking around in a physical path in a very small room, but the goal is you want to have a virtual environment which is much larger than the room that they're actually in. And so you want to subtly adjust the world as they're walking around so it feels like they're walking in a large space, but they're actually walking in a small space. And some of the techniques for doing this work as follows. As the person is walking around, you slightly rotate the world during that movement. And in fact, you can, when an eye saccades, so the person moves their eye, or when they blink, you can actually do a large rotation of the world. And the key thing, people don't notice. So if it were the case that we had a detailed 3D model of the world, then it would be really surprising that you blink your eye and after your eyes reopen, the world has shifted, and yet people don't notice. So this really illustrates that we're not storing richly detailed 3D models of the world. So there's this idea called fragmentary vision, 3D vision. This is kind of gaining steam in human perception in recent years. And the basic idea is that we don't store a single consistent 3D model of the world in our heads. And there's this review paper by Paul Linton et al., which is a great summary of these results. And why is that? Well, the argument is that we don't need consistent mental representations in order to perform tasks. We as humans can assume that the world's not going to rotate suddenly every time we blink our eye. So we don't need mentally consistent representations. And then the question in this research then is, how is vision fragmentary? And people have proposed various ways that we have inconsistent representations. Maybe we have different representations for objects at different distances, or for separate objects, and so on. And I think all these things could be true. I'm going to argue that 3D vision is fragmentary across fixations. And what I mean is that at every instant, whatever you're looking at right now, you have a real detailed sense of the shape of that object and its details and colors and so on, mostly in foveal vision. But the moment you blink or move your head or close your eyes or look somewhere else, most of that information and most of that sense of 3D shape is discarded, and you only preserve a high-level, abstracted 3D representation of what you were looking at. So if you look at a plant or a tree, you can see all the veins in the leaves, you can see all the detail in the leaves, you can count them. The moment you look away, most of that information is gone. And you still have a sense that there are leaves there and what their colors were and so on, but you couldn't count the number of leaves on a tree the way you could have when you're looking at it. So I would claim that most of these ideas translates to pictures. The way we look at pictures uses a lot of the same visual capabilities that we use in the real world. So here's an example of a visual illusion where if you look at it and you fixate your eye on different parts of the picture, you can see, so these are, the picture contains two concentric rings. Now, whenever you fixate your eye on different parts of the picture, that you can see that the rings are separated in the part you're looking at, but in peripheral vision, they look entangled. And moreover, you can keep moving your eyes over the picture as long as you want, and the illusion persists. So if it were the case that you mentally stored the entire picture in your head and you built it up over time, that mental representation, then the illusion should go away, but it never does. So this illustrates that pictorial vision is fragmentary across fixations. We never store the whole picture in full detail in our head. So this means that pictorial vision in some way operates really differently from the way a lot of computer vision works. In computer vision, you load a picture into memory, run a bunch of processing on it, and then output a result. In human vision, we never store the entire picture in our memory all at once. Instead, we would look at a picture, maybe you look at one part of it, you get a sense of what one person looks like, and then you look away, and then you see another person, and then see another person, and over time, you maybe build up a mental sense of who's in the picture and where they're sitting with respect to each other and what they're wearing, but you never store all the little details in every single pixel. And in a way, this is why impossible pictures can be interesting, because each eye fixation looks like a normal picture, like a consistent object, but they can't be integrated into a coherent shape. Whereas if the inconsistency is visible in a single fixation, it's a lot less interesting. So to test this idea, we ran an experiment in which we create this wide-angle photo. You can see the objects in the four corners have marginal distortion. We show this to a person. We ask them to fixate on the center of the picture and then move their eye to the upper right. When they move their eye, we blank the screen and show them this picture, and then we ask them, did the picture change? And usually they say no. So what's changed here is that the building in the upper right had its own local linear perspective, whereas in the original, it had marginal distortion. So we ran this experiment multiple times with each of the four corners having the same undistortion when the eye moves to it, and people don't notice the changes. Then, after running the experiment, we asked them, did you see this picture? We showed them a few examples. The one on the left is a picture that we actually showed them, and they say they did not see this at any time during the experiment. The picture on the right has a composite of the four corners that they actually fixated on, even though we never showed them this picture, and they say, yes, I did see that picture. And so this suggests that picture viewing is less like a single experience, but a composite of individual eye fixation experiences. And I think this also can answer the question of why can pictures convey such an effective illusion of 3D when they're just 2D objects? And the answer is that our real-world 3D vision is actually a lot less than it seems. Now, in order to form up with a theory that explains or describes this phenomena, again, I want to motivate it with this picture, and this comes from a paper by Kundrik et al. These are the four authors of that paper. It's a wide-angle photograph, and the question is, how are these people sitting with respect to each other? Are they facing towards each other, away from each other, or are they parallel? And when I ask audiences that usually someone will point out the correct answer, which is that they are sitting parallel to each other. But the interesting thing I want to note here is, so Jan over there on the right is facing to the right, and if I crop the photo, then it still looks like he's facing to the right. So his apparent orientation doesn't depend on the rest of the picture. It's local, just like all the other effects that I talked about. So the hypothesis that explains this and describes the previous hypotheses, I'm calling fixation-centered perspective, and it says that in each eye fixation, a picture is interpreted in terms of linear perspective centered on that fixation. So when you fixate on one part of a picture, you interpret the shape of that around that fixation as though it were generated with a center projection in front of the fixation by linear perspective. And most of the information you get is from the foveal region or nearby. Then when you move your eye, fixate somewhere else, Then in the other part, you also interpret it as it according to its separate linear perspective with its separate center projection in front of that fixation, and so on. And we ran an experiment to test this, which I'm not going to go into details about. It's based on some previous work by Vishwanath and Marty Banks. And it also showed viewers' behavior consistent with the hypothesis and inconsistent with any other previous theories of perspective. So to summarize the hypotheses, there's a sort of, I've described a series of hypotheses that all fit together. Our 3D vision in the real world is fragmentary across fixations and foveal. Shape locality says that our shape perception only depends on the local picture region once we recognize objects. The direct view condition says that regions of pictures do not look distorted if they look like they could have come from a local linear perspective. And this is because of fixation center perspective. We interpret shape according to a local linear perspective in each region. I want to argue that these hypotheses explain the evidence well. They are consistent with foveal and peripheral vision and the way that these things work and the limitations of peripheral vision. They explain why linear perspective has been so effective throughout the centuries, but also when it creates distortion effects, as well as when it creates distortion in art. It explains why paintings often tend to be multi-perspective and why computational projections based on multi-perspective are also effective, and as well as the experimental results it described. And I don't know of any other theory of perspective that even attempts to explain most of these things or is consistent with all of them. So I think this is really the best theory there is for understanding perspective throughout art history and photography. Now that said, of course, there are many unknowns here. We really don't have a sense of how exactly does 3D awareness work over time. What awareness do we have of 3D from after we've looked at a picture or from the real world? And so clearly from these pictures, we get a sense of how people are arranged, who's to the left of whom. In a more detailed picture, we get a sense of who's in front of who and stuff like that. But how rich and how accurate is that information in the head, we don't know. This also gives a different sense of how we think about making pictures. In a sense, one can think of making a picture as like collage. You decide how you're going to depict all the individual objects, and then you also decide you can rearrange them and move them around with respect to each other to make different relationships and compositions of objects in space. So object depiction can be thought of somewhat separately from spatial arrangement. And there's lots of different ways to arrange individual parts of a picture such that they create different compositions in different senses of space and different relationships between objects. So to summarize, I argue that we perceive shape in each eye fixation in a picture according to a local linear perspective. And this explains how we perceive shape and when we perceive things as distorted throughout art history and photography. And as a result, we can think of making a picture as figure out how we're going to depict elements and choosing them and arranging them in 2D. And this is just the beginning of a possible set of theories, and there are many open questions, many more things to study and test here in order to understand how we understand shape in pictures and to make more tools for helping people make better pictures. This work is primarily described in the first two papers described here, and all the papers on this work are available at this URL here, as well as in the notes for this talk. Thank you very much.